Prof. Wole, good morning. Please, could you share your screen so that we see that, or and your slides so we see that everything works? Yeah, thank you. Yeah, we can see your screen. Okay, we can see this. Thank you very much, Prof. Okay, so I'd like to say good day to everybody, and it's good to have you here for this colloquium series of the African Material Research Society. So you are all welcome. So my name is Omololu Akinjo. I'm currently the Vice President of the African Material Research Society, and I'm also the Chair of the Local Organizing Committee for the AMRS 2024 conference that is coming up in next year, December, 16th to 19th of December 2024. We'll be sending you more information about the upcoming AMRS 2024 conference. Unfortunately, the president of AMRS, Professor Balangom, he's traveling back to his country, so he won't be able to join us today. But I'd like to welcome all of you to today's colloquium. Okay, so today's colloquium will be one in a series that we'll be having throughout the year. So throughout the year, we'll be having some other colloquium that will be delivered by different eminent people. But at the same time, also we'll be having some special seminars that will be for career development. So in the sense that if you're a young researcher, you want to know where to get grants, we'll have some sessions for that. And if you're a PhD student, you want to know how to excel in your research, we'll be having a session for that, and we'll be having different sessions throughout the year. We'll make an announcement for this. We plan to have one on machine learning or AI. So if you are a researcher and you're thinking of how to use AI in your research, you'll be having a session that you can key into that will help you in this respect. So at the end, also, I'll remind you again about the AMRS 2024 conference that is coming up next year, December 16th to 19th of December 2024. We'll give you more details as we go along. So without much ado, I would like to introduce our speaker for today. So I think I know quite a little bit about the speaker to be able to introduce him. So our speaker for today is Professor Winston Oluwole Soboyejo. So Professor Soboyejo, he has his PhD degree from Cambridge University in the UK, and he was a full professor at Princeton University, and he also served as a provost and later as the president of the African University of Science and Technology in Abuja, Nigeria. Then later on he moved back to Princeton and then moved to Worcester Polytechnic Institute in Massachusetts in the USA, where he was Dean of Engineering. And then after that, he became provost, and his latest position there, he was also vice president, one of the vice presidents, and then his latest position there was at WPI, was as interim president of the whole university. Later on, he got a position at the SUNY Polytechnic Institute, the US, where he currently is there now as the president of the SUNY Polytechnic Institute in New York, USA. Okay. So in addition to all this, Prof. Wole has been the chair of the board of the African Material Research Society. He's a seasoned material science and engineering person, so science and engineering. And he has mentored many of us that are currently online. And he has more than 30 PhD students he has supervised. And in addition to that, maybe now more than 40, right? Right, Prof. Wole? It should be more than 40 now, or maybe more than 50. The last count, it was more than 30, but now I think it should be more than 40. And he has mentored many of us, okay, both formally and informally. So he's passionate about Africa and about using materials for development and advancement of Africa and of people in Africa. So thank you very much, Prof. Wole, and over to you.
Thank you so much, Omololu. It's a real pleasure for me to be here today and to share with you sort of my own passion for how we can really use materials for African development. And before I go on, I just want to really acknowledge, I hope this thing works, the people that I've worked with who have supported my work over the years, because without them, this is not possible. So somehow my system is not advancing the slides. Let's
Okay.
try again. Here we go.
Okay.
So one of the things that I've learned over the years is only way you can get things done is to work with people when you have a vision. And in the 90s, I had this vision where I sort of remembered going all the way back to my childhood, the idea that I needed to really be involved in work that uses materials for African development. At the time, I was working in the aerospace industry, but my mother, who's shown there on the bottom right, who's now late, sort of asked me, what is the implication of all the work that you're doing for the development of our people in Africa? And I couldn't answer that question when I was focused only on hypersonic aerospace issues. And so from that time, I started to think about how to do research that's relevant to Africa. But then I also realized that I couldn't really get things done unless I link up with policymakers, people in government. And so I started collaborating with people in government. So I show pictures there of President Obasanjo and Ban Ki-moon. And it was interesting because initially when these relationships started, um, I just thought, well, I'm just a scientist or an engineer. What difference does this make? And it turns out that I was able to see that when you bring a scientific perspective to many of these people, you can actually get things done on a scale that is bigger than what you can do with your science alone. And so serving on Ban Ki-moon's advisory board and working with President Obasanjo, what I actually realized was that you can do things that can impact development. But of course, the most critical part of your relationship is very often with the scientists that work with you, right? And so I'm really grateful to all the people that I've collaborated with in doing scientific work that I still continue to do till today. Now, as somebody who became enamored by materials in the sort of early to mid 80s through the excellent teaching of a guy called Anthony Smith, one of the things that I never realized was that actually for almost all major technologies, materials are the major driver. So if you look at airplanes, you would think it's aerodynamics. It's actually materials, high temperature, lightweight materials that are the key. And these days also the ability of those materials to sense and respond. If you look at computers, it's materials that are the key that determine what you can store in smaller and smaller bits that are being driven by nanotechnology. If you look at automotive technologies, it's the same thing. Materials, lightweight materials that are durable are the key. And if you look even in biomedical applications. And as you go from implants to tissue engineering, these are all areas that I've had the opportunity to work on over the last 35 years. But my biggest surprise has just been the key role of materials. And so in thinking about this, in the mid 1990s, I remember writing a pre-proposal to the NSF, trying to ask the NSF, the National Science Foundation in the US, to help support collaborations in the US, between the US and Africa. At that time, I was told that, well, the US doesn't really fund Africa, and that effort was not successful. But later on, after the visit of President Clinton to Africa, there was renewed interest, and I was invited to a workshop in Pretoria, where at the farm inn in Pretoria, a number of folks from Africa and the US came together and developed some ideas on how we could work collaboratively across those two areas. And out of that was born a US African Materials Institute, USAMI, that started to bring scientists and engineers from Africa to Princeton, and later grew into many, many more activities that mushroomed into the Africa MRS, and also a number of activities that persist until the current time. So if I look at the time that has passed from the farming experience in about 2000, 2001, to the first meetings of the Africa MRS in Dakar, to the visits to Princeton, which is what's shown in the top right, and then to the establishment of the African University of Science and Technology in Abuja, AIST in Arusha, and all of the things that have been done to develop people with a focus on development. What I'm going to try to do today is just to show you how we've gone from this vision that is much more than just an idea to working with people to really realize the society. And so here I'm showing you some pictures of some people that were involved in the Africa MRS from the very onset. Professor Bay organized the first meeting in Dakar. And at that meeting, we had people like Frank Nabarro from WITS. Frank is one of the greatest materials researchers of all time, who wrote classical books on dislocations. People like Yunus Balim, Professor Olusegun Adewoye, who was the first African to get a PhD in material science from Cambridge. Leslie and Malik Maza, and so many wonderful people that really were there at the beginning. These folks basically imagined the idea of the Africa MRS as a society that will bring together the knowledge that's needed to realize African potential. And that group, of course, goes on, till more recent times with people like Professor Balangong, who's our current president, Sam Chigoma, who was our most recent president, and eminent scientists such as Sosina Haile and Anjan Zhou, that have really come together working with people like Eric Garfunkel and others to really build the African Materials Research Society into what it is today. But I would argue that that group really not only needs to exist to organize the society, but it needs to come together to really develop Africa's potential in materials around areas of local need and local and global challenges. And so in the early days, what we decided to do was to work on problems in which we could bring the field of materials to address our challenges in health, in water, in infrastructure, and in energy. And this came from really significant exchanges that occurred at the beginning. And if you think about it, if we can use materials to address these challenges, then we have the opportunity to solve many of the problems that we face as a continent and perhaps even as a world. And so from these early days, there was the recognition that actually in Africa, most people do not die from malaria. Most people die from cardiovascular diseases and cancer. Right now, 22% of all deaths in Africa are due to cancer. By the year 2030, it will overtake cardiovascular diseases, which have about 33% of all deaths. Then the problems of water are associated with contaminated water that people drink. Can we use our materials to address these problems, to remove biological contaminants as well as chemical contaminants? And can we use our approaches in materials to develop the solar cells and light emitting devices of tomorrow, as well as the batteries of tomorrow? And can we use our materials to develop the sustainable building materials that are eco-friendly and reduce carbon emissions in a world in which we're increasingly concerned about climate change? So what this talk is going to do is to give you examples of research that have been done by teams of Africans to address these issues, and talk about how we can transition these into a manufacturing initiative. So many of the people who came to do the work are shown here. People like Grace Oyatogun, or Grace Oparinde, was there in the early 2000s. She's now the head of the materials department at Obafemi Awolowo University. Tom Otiti from Makerere University did some work which was considered by the head of the NSF as a great example of how African scientists can contribute to global science. Baba Tokwe from Ife, and many others from across many African countries. A total of 36 African countries participated in some of these early USAMI visits. Now, what also came out of this interaction was a network of what we call the sort of Pan-African Nelson Mandela institutions. And it turns out that in the early days, in the early 2000s, the head of the World Bank, Jim Wolfenson, had a conversation with the African heads of state. And at that meeting, he asked what was the single thing that the World Bank could do to develop Africa. Sitting in the audience was Nelson Mandela, and he said, invest in science and technology. And so in the early 2000s, the World Bank head, who was also head of the Institute for Advanced Study in Princeton, then convened a number of studies in which I was invited. So he convened a meeting where basically we started thinking about what would those institutions... Could you please mute yourself? Homolulu, can you please mute that person? Yeah. So at that meeting, the idea of starting these institutes of science and technology across Africa that addressed African problems was initiated. And this led to, of course, the vision of a new campus in Tanzania, in Arusha, which is the Nelson Mandela African Institute of Science and Technology. Another one in Abuja, the African University of Science and Technology, where I served as provost and president for a few years. And all of these were made possible by collaborations with the presidents of those countries who bought into the vision of the role that science and technology can play in the development of Africa. And working with people like Philip Griffiths from the Institute for Advanced Study, President Obasanjo, Minister Ngozi, and others, this vision was realized. And it's interesting to see how these kinds of visions really enable the development of people. Here I'm showing you the vision of AUST and the current site in Abuja. Sitting in the audience are people like Benjamin Tufo and others who now have their PhD degrees and are now working as professors at African universities. Omololu asked me about the number of PhD students that have graduated. Like many good African fathers and mothers, I don't count my children, but I can tell you that the number is over 70. So many of these people are working at our universities, training the numbers of students who are now making a difference in the world. Interestingly enough, some of our students that have gone beyond the shores of Africa are now being hired at universities across the world. One of the graduates is now a professor at MIT, and Elijah Jusu, and there are others that have been hired at universities across the world, showing that we can really do excellence in teaching and research in an African context. Also, along with this vision of sort of excellence in Africa, the vision of a new African Silicon Valley was born. And this vision is to use the region between Mount Meru and Mount Kilimanjaro as a nucleus of a new center of excellence. And that new center of excellence that was funded mostly by the Tanzanian government with aid from a few other countries has given rise to this campus that is now training people with excellence in materials and also in the life sciences. And so if we look at all of this, we see that we've set ourselves up for the potential to do world-leading science. And so the question is, can we start from where we are and grow in the context of collaboration with the diaspora in ways that leverage technology, in ways that leverage collaboration and interdisciplinary cooperation for the next generation. And of course, we are now in the age of AI, we're in the age of the fourth industrial revolution. And I want to give some examples of how we can leverage those approaches in applications to cancer and also in applications to the development of renewable energy opportunities. So let's start with cancer. Why cancer? Cancer is important, and in particular, breast cancer kills more women than any other type of cancer. And if you look at the case of breast cancer and cancer in general, there are two problems. One is the problem of early detection, and then the other is the problem of treatment. The existing methods are very severe in terms of their side effects, and we want to think about other ways in which we can address these problems. Now, one of the things that we've done is to look recently at repositories of breast cancer images. And so when you look at those repositories of breast cancer images, which can represent thousands or tens of thousands of immunohistochemical images or optical images or MRI images, in this case, what we find is that those images often are presented with different resolutions. And so by basically analyzing those images with different levels of resolution, you can create a bag of multi-resolution convolutional feature representation. And as you create that information stack, what you then enable is an increase in the accuracy of the detection of the cancer to extremely high levels. And so this is work that was done with Emmanuel Agu and David Clement. And as a result of this work, we basically were able to develop different models for very highly accurate detection and also very sensitive and specific detection of breast cancers. Now, you might then say, what about the case of African context? And can we begin to build those databases? And so we've been working with people at the National Hospital in Abuja, where we're basically looking at breast tissues that are extracted. And so if you look at those breast tissues in normal people, you see that the tissues are intact and the boundaries are very clearly intact. As you go from normal tissue to grade 1 tissue, you see that the structure begins to break down. By the time you get to grade 2 tissue, you see that the structure breaks down even more. And so essentially it's clear even from the optical images that you can see changes in the evolution of the structure associated with the evolution of the cancer as a disease. If you now look at higher magnifications using atomic force microscopy to look at those tissues, what you basically see is that for the normal tissue, you have this actin cytoskeletal structure that's intact and well distributed. But as the cancer begins to progress, that actin structure that holds the cells together and gives them structural rigidity begins to degrade and disappear. And as a result of that, one would expect that over time, the loss of that actin structure results in lower stiffness and perhaps also lower viscoelastic characteristics. And so in doing this, one can now begin to do viscoelastic probing using indentation. And when you use indentation, you can actually see that the Young's modulus of the tissues decreases drastically from normal tissue to grade 1 tissue. And the degradation in the Young's modulus continues as you go from grade 1 to grade 2 to grade 3. A similar thing is true for the viscosity of the tissue. That also decreases as the tumor progresses, which means you can have mechanical probes for the detection of the tumors in ways that can complement the visual methods for identifying the tumor. Similarly, if you look at the receptors that are expressed in the tissues that Africans have, what you find is that the receptors that are expressed are not the typical HER2 receptors, but receptors such as LHRH receptors, luteinizing hormone releasing hormone receptors, or ephrin A2 receptors that tend to be overexpressed as cancers evolve in Africans. And then if you look at the adhesion to those receptors, that adhesion tends to increase with increasing grade of tumor. And similarly, the adhesion energies, the contact areas, and the contact forces all increase with increasing tumor development. So what this basically means is you can have mechanical probes that measure contact radius, contact area, as probes that can become adapted to the detection of a tumor, in addition to the visual methods of detecting the tumor. Now, going from those kinds of efforts to validating other kinds of nanotechnological approaches, one can begin to use experiments on mice to really explore different ways of imaging cancer and treating cancer. And so in doing this work, we can inject the human version of the cancer into the mouse. That human version of the cancer basically enters the bloodstream and then eventually goes and induces the tumor in the body of the mouse. And then the tumor can develop at the accelerated life rate of the animal, which means that in 2 weeks you have early stage tumor, 3 weeks you have mid-stage tumor, and 4 weeks you have late-stage metastatic tumor. For each of those stages, you can then inject nanoparticles, and if those nanoparticles are targeted nanoparticles, they will go and attach to the specific tumor region that you're trying to target. And so in this case, we're showing you the results of the LHRH conjugated to magnetic nanoparticles. And what you can basically show is that you increase the contrast of the tumor in the domains in which the nanoparticles attach. And essentially, for 1 centimeter wide tissue here, what you're basically showing is that you have millimeter or sub-millimeter resolution in the detection of your cancer. Now, if you can target with the LHRH with the nanoparticles, you can also do so with drugs. And so we've taken some cancer drugs, prodigozine and paclitaxel, and conjugated them to LHRH. And when you conjugate these to LHRH, the LHRH targets the LHRH receptors in the tumors, and you can target early stage, mid stage, or late stage tumors. And so with those targeting motifs, what you can basically do is, if you look at the images in blue and green, you start with a tumor after 2 weeks. When you inject the drug that's targeted, you eliminate the tumor in about 8 days. So with methods like this, you can target and eliminate tumors. You can reduce side effects and toxicity effects of the treatment. In the absence of those targets, you basically have the tumors growing, leading ultimately to death. So by targeting then receptors we find in African patients, it turns out that you can be more precise in how you target the cancers, you can eliminate the cancers, and you can do so whilst reducing the side effects associated with those treatments. And so we're currently working with the team in Abuja to go from here to the next stage, which is to try to demonstrate this in people. Now, interestingly enough, you can also, of course, release the chemotherapeutic drugs from gels. And so what you can do is you make these gels that soak up drugs, or you can make these polymers that soak up drugs. The problem is that in most cases, they release the drugs in 1 or 2 days. But in this case, you want them to release the drugs over 90 days. And so to enable that to happen, what you need to do is you need to look for extended release of drugs with different kinds of gels or polymers. And once you trigger those can then release the drugs in ways that can be triggered by temperature or pH. And as you do this, you basically can then deliver the treatment locally, thus reducing the amount of drug you need to have a therapeutic effect. And so here we're showing some results of scaffolds that we've made, where we basically can release the targeted drugs, the LHRH conjugated drugs, from these scaffolds. And when you release those drugs from those scaffolds over a period of 90 to 120 days, you can prevent the recurrence of the tumor in the cases where the release of the drugs is localized. And the other thing that you can do is you can then facilitate the regrowth of tissue on those polymeric materials using tissue engineering approaches. And so you not only stop the recurrence of the tumor, but you regrow the tissue. And we've done this for release from microscaffolds, but we've also done this for release from microparticles. Again, 90 to 120 day release, which prevents the recurrence of the tumor, and then you regrow the tissue around these in a way that allows you to do healing of the region. And by the way, with these tissue engineering approaches, one can extend them to diseases beyond cancer. And so we've been working with Mona Marais for a number of years in Alexandria, Egypt, to develop laser textures and RGD coatings. Most recently with the work of Sarah Osafo, which builds on the work that went to human clinical trials in Alexandria. What we find is, in addition to the laser textures, we're able to introduce new methods of obtaining hydroxyapatite from eggshells and also from bone in ways that dramatically accelerate the initial stages of wound healing. And so in this work, what we basically show is that cell spreading during the initial stages of implant integration, which often takes between 1 to 7 days, can now be achieved in less than an hour using nanostructures that are introduced by methods that were developed in collaboration with Sarah Osafo of the University of Ghana. So what we're basically showing is that there's a dividend that's coming from the investments in our biomaterials efforts. And we're giving value to materials in ways that are leading to new implants at the nanoscale, at the microscale, and at the macro scale. So I want to shift gear now and talk a little bit about the need for alternative ways of obtaining energy. If you look at what, of course, the emissions from all sorts of energy factories are doing to the world, we need to clearly find green energy approaches that are ubiquitous. In the case of Africa, we also need to make sure that that energy is affordable, because many people, of course, live on less than $2 a day. So the obvious answer, I think, is to look at what happens to the world at night. If you look at the world at night, what you see here is that many places in the world have electricity, but Africa is dark. And so, of course, there are metropolitan areas that have electricity at night. So the question is, how can we really address this issue? So if you now look at the map of the world during the day and look at solar radiation, what you find is that those places that don't have electricity at night have significant amount of solar radiation. So we call this the map of possibilities. So the question is, can we then develop the solar cells? And so we started about 20 years ago making really poor solar cells with efficiencies of about 1%. And the story I'm going to tell you today is going to be a story of how we went initially from making LEDs to solar cells, and to solar cells that now have efficiencies of about 23.4%. And so in the early days, though, the initial work was on LEDs with Stephen Forrest, where we basically figured out that by applying pressure, you can transfer patterns onto the surfaces of substrates. And those patterns you transfer are like pixels on a TV screen. That work on the stress-associated stamping of these patents resulted in a patent that was licensed by Samsung. And that patent is been the patent that guides the development of the cold welding processes that are used to pattern the electrodes and the pixels on these LED structures. Now, the question then is, can we take that same kind of idea of pressure-assisted fabrication and apply it to other layered structures? And so if one thinks about, for example, perovskite solar cells or perovskite LEDs, one can begin to play with these ideas. And of course, as you apply pressure, what happens is you deform around impurities at interfaces, and you might densify some porous structures and improve contacts at interfaces. And so if that works, then you should see changes in the power conversion efficiencies associated with the different pressures. And actually, as you apply pressure, what we find is you close up voids, and up to certain pressure levels, you see that that increases the power conversion efficiency, say from about 17.5 to about 23.5 with a pressure of about 7 MPa. But beyond a certain pressure, you start inducing cracks. And once you start inducing cracks, you degrade the devices. But basically, through this method of pressure application, you can increase your efficiencies for some FAI perovskite solar cells up to about 23.5%. And so with methods like this, one can now start asking, can we now use different methods to spray the solar cells? And can we guide these processes with AI? And also we can ask the question, what is the sort of theoretical efficiency that you can achieve? And so if you look at the Shockley-Queisser limit, basically tells us that the maximum efficiencies we can achieve are of the order of 32%. The world record efficiency today is about 25.7%. And so what we're now trying to do is to see if we can increase on the levels of efficiencies that we've achieved using machine learning and AI to guide our efforts. And so we've been working with a team of machine learning and AI experts, Radhika Niamtu and Stephen Price, and one of my former students, Rashia Chwani, to really develop methods that look at ways of optimizing the parameters that improve the efficiencies, and also looking at the defects that are associated with ground truths and model predictions at different stages of degradation of the devices. And through these methods, we're predicting the potential to have devices with efficiencies that are as high as 29%. And so these methods are now guiding our processing efforts. Now you can do all of this and make solar cells and make LEDs, but actually the big question is, what difference does this make to the lives of our people in rural Africa where these technologies are needed? And here I'm showing you some work done in Impala in Kenya, where we basically looked at what would happen if we could introduce LED lighting with solar cells that are 2 to 5 watt solar cells. And what difference would something like this make? The advantage of these two examples, one is a retrofitted kerosene lantern with 6-volt batteries powering LED lights. The other is a more sophisticated system that still has 6-volt batteries and a 2 to 5 watt panel, but looks a little nicer. One costs about $24, the other costs about $45. Now, the important thing is what actually happens to communities when you take technologies like this and you bring them to those communities. And this is what you see. So even with those modest achievements, this kind of approach blended with methods to make them affordable to the communities that need them actually results in major transformation. So we went, in this case, to this village which had 200 homes, where basically the people paid for these over 12 months, $2 to $4 per month, which was their energy budget. And as a result of this, developed a sustainable way of using solar power and LED lights to address their energy needs. And the transformational impact that it had on their lives was just incredible. If you look at how they felt as a result of using this, most people really liked it. They felt that the lantern and the presence of electricity brought civilization to their village, and they felt that the impact of this was just to make them feel much better about being where they were. They stopped using kerosene, which was giving them pulmonary diseases. And so within a short period of time, the kerosene lanterns were retrofitted or abandoned. Now, if you go further, you start realizing that the key in many of these things, and as we move into the electric vehicle era, the key is whether we can make energy storage capability that's affordable and that is efficient at storing energy. So we've taken the idea of pressure application and extended it to the development of lithium-ion batteries. And so here, what we basically show is that we can make these aluminum dope mixtures of LLZO-based batteries with all solid-state electrolytes. And if you apply pressure, you increase the contacts across those devices, and you also increase the energy storage capacity and electrochemical phenomena. And so here we're showing you strain maps associated with pressure application. And of course, as you apply that pressure, you improve the performance of the batteries. But if you start inducing cracks, then beyond a certain pressure level, you degrade the batteries. So we've simulated those stress distributions associated with contacts. This is the work of Mobin Van Daddy, working with John Aja in our group. And we basically shown that once you reach some critical pressure applications, you start forming cracks. And those cracks evolve as you increase the pressure, which ultimately degrades the devices. And if you look now at the Nyquist plots, you can basically show that as the cracks form, you basically degrade the batteries. And similarly, you can simulate the effects of contacts on contact resistance and contact areas and show that initially as you increase your pressures, your contact areas improve and your device performance improves. But beyond a certain point, you start getting the fact that you start inducing cracks. Now, what's interesting is that when you charge and discharge your battery, although you are doing electrochemical phenomena, what you're actually doing is also embedding ions in traps and inducing local variations in strain. And so if you look then at strain mapping as a function of cyclic discharge and charging, what you find then is that you induce significant strains during charging, but the strains are even more during discharging. And those strains that are induced actually then cause cracking. And it is the evolution of these cracks due to cycling that leads to the degradation of your battery. So using methods like this, we're able to develop really remarkable, stable lithium-ion batteries with very significant charging capacity. And so this now gives us the hope that we can now leverage these methods to begin to now scale up to ways of transitioning these kinds of studies to really making real batteries that can be used in vehicles. And so as we do this work, what's important to learn here is that as we charge and discharge, it's not just electrochemistry that's going on. There's a lot of mechanics that's going on, giving rise to strain evolution, giving rise to cracking. And as those cracks evolve, resistance increases, ionic conductivity also changes in a way that we must understand as we optimize these structures. Now, before I finish, I just want to touch a little bit on materials for sustainable buildings and green materials and multifunctional materials that are interesting. So obviously, cement is one of the biggest contaminants in that it results in about 7% of global carbon emissions. And so one of the things that we've been doing is to use mushrooms, fungi, to basically interact with laterite particles to form building materials. And depending on the amount of laterite materials that you introduce, you can control the stiffness, you can control the strength of these materials in ways that give rise to green materials that are carbon negative materials. And so we've been studying those as functional materials, and we've been doing this work with a guy, Precious Etinosa, who's done some remarkable work to show that we could make green building materials that are multifunctional using available earth-based systems. We've also been inspired by an idea that was really originated from the late Professor Adewoye to look at how we can use cassava to basically strengthen materials. Originally, we thought because cassava contains carbon and nitrogen, that the carbon and nitrogen will form carbonitride, which would then enable us to basically have carbonitrided surfaces that are a sort of high strength fatigue resistant surfaces. But what we actually found with the work of Tabiri Asumadu and Desmond Clenham was that when you actually process these materials with these cassava leaves that are dried at particular temperatures, you actually nucleate and grow graphene on those surfaces. And so through a process of introducing the dried cassava leaves that are processed in particular ways at high temperatures, you can actually grow graphene structures with well-controlled nanoscale dimensions. And you can do these on steels, you can do these on titanium alloys, you can do this on nickel-based superalloys, and you can even do these on high entropy alloys. And so we've done these, and what we find is that those graphene surfaces actually have really low friction coefficients. And so when you have materials with really low friction coefficients, they lend themselves to many, many applications where you can now begin to reduce energy losses associated with mechanical systems. In addition to that, they also have really low wear rates. And so by using these methods, we can not only reduce friction, but we can also reduce wear. And so we've done basic studies of wear that basically show that you can get abrasive wear up to some level. And in some cases, there's evidence of adhesive wear, especially when the oxides bond and adhere. And we've basically shown that as a result of these kinds of efforts, we now have these ultra low friction surfaces that can be introduced into all sorts of green engines, either automotive or aerospace, in ways that are very significant. And here are some examples of some of the applications that we envisage as a result of this kind of work, where you can see that you can make ball bearings, you can make coated pistons, you can make all sorts of interesting mechanisms. And the key here is that we have this scalable, easy to use method of carbonitriding that allows us to actually introduce graphene. And then most recently, we've started looking at how do we extend this to doing graphene-based photonics and graphene-based microelectronics in ways that we will report at a different time. Now, before I finish, I just want to say that in many ways, Africa has this rich array of minerals. But what we need to do is to transition these minerals from just potential into industry. And so if you look at the minerals of Africa, lots and lots of minerals. But really, it's the example of Dangote that shows us what we need to do, which is to take those minerals and not just do research, but to really transition the knowledge from the research and development into manufacturing at scale that creates wealth for communities, and to take many of the ideas that we've talked about in the earlier stages and say, how do we make those batteries? How do we make those solar cells driven by the knowledge and the capacity we have from doing the research and the people we train in ways that transition us from a continent that's rich in mineral resources and agricultural resources to a continent that adds value to these resources in ways that create jobs and opportunities for those that lie within. And my biggest hope and dream is that within every African country, all 54 of them, that we have 10 Dangotes that can take these minerals and take these ideas and take this research and take this knowledge and transition it into industry that truly adds value. And it's not just material resources. If you look at the energy resources of Africa, we're truly blessed. As you go from the Gulf of Guinea across from West to Central and Southern Africa, you have 10% of the world's known oil reserves. In South Africa, we have coal, we have many natural resources, gold and platinum. And across the other side of Africa, in the eastern part, they've discovered oil in Mozambique, Tanzania, Kenya, all the way across to Sudan and Niger. We have geothermal energy. But what we really need, of course, is how we leverage all of these energy resources and add value to them through our use of science and technology. And it is my hope that as you listen to this talk and you see what we've done in the last 20 years or so, that we all recognize that materials really represents the field that is pivotal and essential for African development. And in many ways, Africa has the materials and the energy resources. But we need to come together and go beyond research. Of course, in the research, I gave you a few examples of how we've worked on methods for cancer detection and treatment, how we've also worked on implants and coatings and tissue engineering. Now, that work has produced good people, but we really need to transition this into industry. Similarly, in the work on energy, looking at solar cells and LEDs and batteries, yes, of course, some of the work has been licensed. Yes, some of the work is used. But there was nothing that would give me greater pleasure than to see us take that knowledge and the human capacity within the AMRS and start thinking about how we transition all of this capacity into industry. And then most recently, the work on making graphene and super lubricious surfaces with ultra low friction has created, I think, an opportunity for us to look at many mechanical components in automotive and aerospace and other applications and start thinking about how we make those structures and coat them in ways that allow us to leverage the capacity we have from this new scalable method of making graphene. And in doing all of this, the real lessons for me are that all of this is only possible through interdisciplinary collaboration, through teamwork, leveraging theory and practice in ways that allow us to go from ideas to markets. But we have to make new friends in business, in industry, in foundations, in government and policymakers to connect all the dots. And I think as we do this, we have to realize that we only really have sustainable solutions and development when we inspire our people, all generations, and empower them to use engineering, science, and innovation as engines of their own development. It's not enough to import and use technology. It is, I think, our greatest imperative to think about how we can leverage our integrated research efforts to really use material science and engineering as the engine for Africa's development. And like the Asian tigers before us, I really look forward to the emergence of an Africa in which we will have the next generation of African lions. And so with that, I'd like to conclude my talk. I'll be happy to answer any questions that you might have. Thank you very much.
Thank you very much, Prof. Wole. This is very informative. So thank you for the information and thank you for all the work that you have been doing in Africa and also in the research area. Yeah. So like Prof said, we'll take questions. We have time for a few questions. You can unmute yourself and ask questions. If you like, you can also type it in the chat. We'll try to read, and but you can unmute yourself and ask questions. You could just put it in the chat and we can ask, or you can unmute. Yeah, Prof, let me ask you a quick question. The work on the carbonitride. So yeah, you said it can scale. How do you think this will scale? Because you need the cassava leaves, right?
You need the cassava leaves, which are currently waste materials.
But do we
Uh,
have enough to be able to scale it? And
I think the answer is yes, definitely yes. So one of the things I've been doing in an African context is actually on the outskirts of my hometown in Abeokuta, actually start playing with, what's the scaling that you can have. And so it doesn't take too much to set up a small environment where you start coating pistons and coating mechanical components on an industrial scale. And the amount of cassava leaf that you need to put together and dry is actually at the level where you can do this and scale from those origins to much larger levels. So it's an interesting approach. Unlike many of the methods where you may have to have plasma and all sorts of complicated environments, it basically is very scalable and very doable in our own context. And it can start small and grow to medium and larger scale in a way that is practical. So I think that there are opportunities for us to think of methods like this that enable us to think about industry.
okay,
And
so
and by the way,
yeah,
yeah,
I was going to ask, are you thinking of like taking the cassava leaves and producing the carbonitride, and then we ship it to the people that are doing the hardening?
no. I'm thinking about taking the cassava leaves,
Yeah.
making the components, carbon nitride in them, and adding value to them.
Okay.
I think we should forget about all these ideas where we take our raw materials and then send them to someone else to add value to them. That's not the goal. The goal here is to say we can design the components, we can coat them, and we can truly add value to them. And by the way, we have on our roads several hundred millions of cars that need this kind of coatings in ways that reduce fuel consumption, in ways that enable us to truly add value. And then we also have countries like South Africa where they manufacture cars and export them to Europe and other places in the world. So, what I think we should be thinking about is how we develop these methods and work to transition them to real manufacturing and scaling.
Okay. Yeah, thank you very much, Prof. Actually, some of the questions in the chat are like this. So Isaiah is asking, how can the government across Africa develop the infrastructure for STEM education of the 21st century, especially practical and experimental research into solving these problems? Um, so
I
related
think one of
question,
the
go ahead.
let's do one of so I think one of the things that was started in the last 10, 20 years has been the effort to invest in centers of excellence, or what I would call centers of emerging excellence. And it's going to be critical that we continue along that path, but we also build bridges between those centers of excellence and industry. And we build bridges between those centers of excellence and key areas that really formulate and implement strategy. So, in many ways, I think we've started those efforts, but there's a lot of work to do to ensure the effectiveness of those efforts. So, let me give you an example. If I look at a country like Singapore, not only do they have these centers of excellence that are well funded, but they also have these groups that come together to think about strategy for Singapore, where they bring the best and brightest people to ask the question, what does Singapore need to look like 20 years from now or 10 years from now? And who are the partners we need to bring in to achieve these strategic goals? And I think in the same way, we need to go beyond the centers of excellence to really bring in these strategic groups together to position ourselves, for example, in clean energy solutions or in transportation solutions or in health solutions, not just be content with just achieving the metrics of the West today, but really be thinking about how we leverage those think tanks into a strategy that achieves our goals in the next 10 years through a leapfrogging process that jumpstarts us into the future.
Okay. Yeah. Thank you very much, Prof. So Chiamaka has a question which is related to the question of Colette. Chiamaka says, thank you, Prof. Do you have any practical steps on how individuals can begin to move from research to implementing these results into the industry and our immediate environment, considering the current African scenario and its associated challenges? The question of Colette is similar. Through which way do you think we can establish materials industries? I mean, for me, one of the things I'll add is, should we wait for the government or should we have the private people do it, or a combination of both? Yeah. Stella has her hand up, but if you take these two questions, then we will take the question from Stella.
Yeah, thanks, Jamaka, and it's good to hear from you. I think we need to start dividing ourselves up more into private ventures and initiatives and see the government more as an enabler than an actor. And so, for example, there's a group I'm working with that's raising $300 million to invest in startups. They're basically investing in startups in in technologies that are non-IT based, right? So
Material.
deep. And so what we need to do more and more is to get ourselves together around ideas where the technology is now emerging and form these startups around African resources that can scale. So for example, right now, one of the biggest opportunities is in battery technology. And actually, across Africa, we have many of the raw materials that are needed to make lithium-ion battery technology. But we don't have many African startups that are exploring this as a possibility. And so somebody like Chiamaka, who I know has some experience here, needs to be thinking about how do you pull together the team, right, that can take some emerging technology, that can scale it and make batteries, and that can look at recycling opportunities and that can take them and scale them and make batteries to serve our needs. Because in the next 5 to 10 years, a significant fraction of cars on our roads will become electric vehicles, and the demand for those batteries is going to go up. In the next 10 to 20 years, a significant fraction of homes will be solar powered. And we need to be thinking again about the battery technologies, about the solar technologies, the different types of renewable energy platforms that need to be part of that. So forming ourselves into startups, gaining access to those funding vehicles is important. And that's why for me, for example, I remember my last visit to somebody like a President Obasanjo was to really look at how do we bring the key investors from Africa to fund that fund in a way that will fund our innovators to establish these companies. And by the way, as those companies get established and become successful, for each company that hires one person, you probably affect the lives of 10 people. And so I think that this strategy of really thinking about ourselves, not only as academics and as researchers, but as people that connect to industry and startups, is absolutely critical in this next phase. I don't think it's just a case of just doing more research to do more research. And then similarly, there's some non-materials types of approaches, such as the AI approaches, where the knowledge that we have from the detection studies can translate into software that has local and global value. But again, we need people to start forming clusters around those, developing those software, marketing those software, getting them used in hospitals in ways that create, again, true value. So I think for the first 20 years or so of the African Materials Research Society, we focused a lot on research. But what I hope that the next generation will do will be to harness that research and knowledge and focus on translation to impact in our own context in a way that gives value to the labor and the capacity we have in terms of resources.
Thank you very much, Prof. This is good. Dr. Stella Bezin-Wachuku has a question.
Stella, how are you?
I'm good, sir. Good afternoon.
Nice to see you.
Yes, thank you for your wonderful presentation as always. So, please, I have a couple of questions. So, first of all, so I'm one of your products, and most of the research that I have been able to accomplish were majorly did in the US. But now, since I came back, we try making efforts to set up a seminar lab. So we have a lot of challenges in Africa. So I don't know how, like you're talking about developing material science in Africa. You see that down here, it's not easy. Things like experience it has it's not easy at all. Taking an example of where to characterize material. In my lab, we do tissue engineering work. We try to make some scaffolds and all that. But the challenge are nanoparticles. But the challenge remains how to characterize them. The other time they said they have SEM in Katsina State. The result we got there was very terrible. It's not something that can be used anywhere at all. And so that becomes a challenge. Then I've been making efforts to set up a second lab, which have been assisting me with. But the problem down here, electricity challenge has not made that possible at all for more than how many years now. And so these are the challenges we face in Africa. Now, I don't know how you will help those of us in Africa, or especially in Nigeria, to get started. Like all those work we have been doing, we're supposed to by now should be pushing them to hospital or pushing them into use in Africa. But you see that most of the results we have are only done in America. But none, we can't repeat them here in the country, which is not helping the research in Africa or in Nigeria. So I don't know how you may be of help. Is AMRS going to set up a central lab if we need to characterize materials, or where we have steady light and all that? Even AUSC has SEM, but due to lighting system, the thing broke down. The same thing goes with Sheffield. So if we can set up a central lab where we have steady lights, so that these things when we have anything, we can use it as a central place where you go there, your work will get done. So that is
Dr. Stella, so I second that, and my own suggestion is that AMRS should set it up in Rwanda. So, Prof, please answer the question.
I mean, in Africa, so that if my work is ready, I can now think of how to take myself to Rwanda or how to send my samples there. So that is my question.
Yeah, so Prof, please answer the question.
Yes. Thank you, sir.
Yeah. So thank you, Stella. I appreciate this question, and it's, to be honest with you, it's been very challenging, because as you know, I spent 4 years in Abuja trying to set up the lab, right? And for a while there, we were able to solve a number of these problems in electricity and water. And I know how much effort it took to get those up to speed and get the students going. And so it's been difficult for me to watch those things left alone, right? And to be honest, a lot would depend on the management of those places and how they solve those problems, which are non-trivial. But what I'm left with now is the idea that I need to set up another lab and really work in a place where things can work. And so actually a key part of this is that. And so Rwanda, quite honestly, in my opinion, is one of the beacons of hope in Africa. It's a place where things work. It's a place where there's very, very clear and consistent government support. And at least for now, it's a place where I think some of these solutions can be explored. And so maybe what we need to do is start looking at places like Rwanda to set things up. At the same time, to be honest, I don't want to give up on the other places. And maybe what we can do is form a working group and just figure out how do we go back and solve those problems, because the problems of electricity were there 10, 12 years ago when I was in Abuja, right? But we figured out a way of solving them and we were able to get things to work. We now have all the XRD, all the SEM, all the equipment you could imagine, basically sitting there. And we need to figure out a way of making sure that that investment is not wasted. And so I don't have the magic bullet, but I would rather think of forming a team of us that begins to think about just how we address the real problems. And then secondly, quite honestly, in bringing the funds to control this kind of activities, we need a different entity that will really allow us to organize and implement. And this again is something that I think the AMRS might be able to play a role in. And it's something that I'm currently discussing with a number of stakeholders that want to fund that kind of effort. So we need to go back to the drawing board because I think the existing structures are not working as well as we would have liked them to. And I welcome your role in this effort. And I do think that Rwanda is one choice where things do work and we have the opportunity to do this if we choose to.
Thank you very much,
Philbert.
Prof. Yeah. Philbert has a question. That'll be the last question. But before then, before then, Musa Abdullah has a question. What do you think Ghana will do to enjoy the full benefits of its lithium resource, which was discovered recently? So this is a question from Musa Abdullah. What do you think Ghana will do to enjoy the full benefits of lithium resource, which was discovered recently? Yeah.
I think it's not enough to just discover the resource. There has to be an intentional effort to set up lithium battery production capability. And there has to be an intentional effort to link up with Ghanaian universities that can support that, not just with human capacity, but with research and development activities. If they don't do that, other people will come in, extract the lithium and export it. And that material has no real value to Ghana if that's what ends up being done. So people like Musa, who did their PhD working on lithium ion batteries, need to come together and form a practical space. They need to go and interact with the government. They need to interact with their universities to make sure that they become a center of excellence for doing this. And it's absolutely critical to do this not just for lithium, but for other mineral deposits. Philbert.
Okay. Thank you, Philbert. Yeah.
All right. Thank you, Prof. Thank you. I'm happy to see you again, Prof. Wole.
No, it's very nice to see you too. You
know. Yeah. Well, I don't have a particular question. I just want to come back slightly on that interaction. Just to mention that actually Rwanda is open to any kind of I would say investment, either intellectual or financial investment, and actually the necessary is to be done for the success of anything. I think those are kind of things that we can discuss during the MRS in 2024. And if there is any strings to be negotiated, we can do what we can to make sure that thing goes as they are supposed to. I don't speak for the government of Rwanda, but I think they are really open.
You know,
I don't know the
Yeah,
Prof.
Philbert,
Ojo would
yeah.
testify. Yeah.
no,
Yes.
Philbert, you're absolutely correct. But there are other countries like Botswana that are also
Yes,
open.
definitely.
Well, it's hard to enter into Botswana.
Yeah. So I
You have to
think
get a visa and everything. Rwanda, you just pack your stuff. Today you come into the country, no problem. 30
All
days,
right.
you get the visa on arrival. Yeah. So thank you very much, Prof. So we are grateful for the talk and we are grateful for all the comments. So let me remind everybody a couple of things. So one, the African MRS conference will be coming up in December 2024. December 16th to 19th of next year, 2024. There's a pre-conference before the conference. So two important things that will be at the pre-conference. Professor Elizabeth Dickey, who is at CMU in the Carnegie Mellon University, she and her student will be giving a pre-conference on materials characterization. So if you really want to know a lot about materials characterization, then you can come around there. So this will be very good. And then also Professor Dr. Raghu will be there to teach us about entrepreneurship. So these are two of the things that we mentioned before. And then throughout this 2024, we'll be having we'll have a curriculum series. I'll be training in different ways and training in different areas. We'll announce beforehand and we'll have different people talking about different things, how to do good research. Some will be also topical on different research methods and research results. Okay, so I would like to say thank you again to everybody. Okay, Dr. Desmond wants to ask a question. BOE.
Thank you
I
so
brought a question, but I think you didn't find it.
Oh, okay. Thank you very much. Yeah. And then UA Meslier.
Can you hear me?
This one.
Hello.
Okay.
Yeah.
Thank you so much, Prof. Prof, I wanted to ask a question. I want to say, how would we try to consolidate all the splinters of centers of excellence around? I know that Arua, for instance, is a vehicle that we can use. And for instance, Professor Leslie Cornish is part of Arua and is also part of AMRS. How do we consolidate some of those things so that we can have maybe labs that are designed economic blocks of Africa in a way that if you are in Nigeria, the 16 ECOWAS countries can actually set. If you are in Rwanda, you can look at the East Africa. Is there a way that maybe AMR can play this critical role so that we can have pocket of centers of excellence across the economic blocks rather than situating everything at one place where it's very difficult to travel, getting visa to travel to some of these places is difficult. I know Rwanda, the visa issue is sorted, but how do we do this? That is my question to you, sir.
So, Prof, go ahead. I don't know if Prof is still around, but I think he left. Because, okay, yeah. Okay, so maybe we'll send him the question. If you have a question, you could send it to the AMRS, secretariat. And then, so the email you got, you can respond to it and send your questions to the email. Okay, so thank you very much to everybody. And we'll be giving you an announcement on the future seminars and colloquium that we'll be having. Okay, thank you. Yeah.
Hello.
Thank you,
You didn't
Prof.
respond to my.
Yeah, please email your question to the African MRS Secretariat. It seems that Prof left because you know he's president of the university and he's very busy. So he's no more
Okay.
online. I don't see him online.
Okay.
So
Thank you.
email it to just respond to the email that gave you the announcement and then we'll be able to send the question to.
Okay,
Thank you
thank
very
you.
much, everybody. Yeah. Thank you. Thank you, Lebo, for organizing. Thank you.
Aeroplane. Thank